Welcome to the second half of section 4.4. Just to recap where we were, we started with y double prime plus y equals cotangent of x. We got a complementary solution, y equals c1 sine x plus c2 cosine x. So that works the same pretty much no matter what you're doing. We then look at our particular solution, and we set it in this form. Y sub p is v1 sine of x plus v2 cosine of x. And then we get this equation, v1 prime of x is cosine squared of x over sine of x. We just arrived at last time. v2 prime of x equals cosine of x. So let's go ahead and finish this one off, and then we'll talk about, in general, what this thing will look like. So we have to integrate these. So v1 of x is going to be the integral of cosine squared of x over sine of x dx. And it's usually the case that at least one of these two integrals is not going to be terribly pleasant. Okay, so we just have to deal with that. So in this case, it's not terribly bad. We replace the cosine squared with 1 minus sine squared of x over sine of x. And notice that gives us the integral of the secant of x minus the sine of x. Okay. Well, we have to go back and look up your integral for secant. That's going to be my ln of secant of x plus tangent of x. And of course, the integral of sine is opposite of cosine, so we get plus cosine of x. v2 of x, of course, is really easy. That's just going to be integral of cosine, which is going to be sine of x. We then take these two and we plug them back into our formula for y sub p. So my particular solution in this case, it's going to be v1 of x, which is our nastier one, ln of secant of x plus tangent of x plus our cosine of x. That whole thing gets multiplied times our sine of x. And that's the first term. Then we have to tack on our v2 of x, which is sine of x, and times cosine of x. Okay, so you get a fairly messy particular solution here. Looks like we're going to get, I'm not sure you're going to simplify this whole lot. I guess you can combine the sine x, cosine x with that one, but there's not a whole lot to do here in terms of making it look nicer. Okay, so that's the general idea of how to find these particular solutions using variation of parameters. The nice thing with variation of parameters is it always works. The downside is you're going to end up with some pretty messy integrals. So when we can use undetermined coefficients, we want to go that way. Let's show one example of another case where undetermined coefficients won't work. It's not going to be because of the function on the right-hand side being something like cotangent. Instead, we're going to take something that does not have constant coefficients. And if you're following along, this is actually number 23 out of the book. So let's go ahead and take a look at that. Now, before we write that down, let's remember what our basic formulas are. v1 prime, if you look what we had, it's going to be 0 f of x y2 prime over the Wronskian, which was y1, y2 y1 prime, y2 prime. Okay, where y1 and y2 are the functions out of your complementary solution. v2 prime is going to be y1 prime in the first column and our 0 f of x in the second column. And then, again, our Wronskian down in the denominator. Okay, the nice thing is this does work when you have variable coefficients. So let's take this equation. So we have x times x minus 2 y double prime minus x squared minus 2 y prime. And then we have plus 2x minus 1, 2 times x minus 1, times y. And that's going to equal 3x squared times x minus 2 times e to the x. Whew, bit of a mess there. Now, the nice thing here is that they give us the linearly independent solutions for the complementary solution. So we're given y sub c is c1 e to the x plus c2, and that's times x squared. Okay, so at least those are nice. And of course, you could go through and check those by differentiating and plugging it in and getting 0 on the left-hand side. So our particular solution, it's going to be v1 of x e to the x plus v2 of x times x squared. And our formulas here apply even though these original coefficients are not constant like you have to have for undetermined coefficients. So let's go ahead and set up our equations. First of all, let's find the Wronskian. That's the easy part. E to the x, x squared, 2x. And that's going to be, looks like 2x e to the x minus x squared e to the x. So it looks like it could get ugly. Hopefully some nice things will cancel when we get to our actual integrations. Of course, since it's a book problem, we know that's going to happen. v1 prime, well, that's going to be my denominator. And I'm going to factor it. And in the numerator, I replace this first column with 0 and my 3x squared times x minus 2 e to the x. And then I have my x squared and 2x, sorry. So finding my determinant, I get, looks like 3x to the fourth times x minus 2 times e to the x over, and I'm going to factor this thing nicely, and we're going to have x 2 minus x e to the x. So the e to the x cancel. So those are going to go away. My x minus 2 over 2 minus x, that's negative 1. And so I get negative 3 x to the 3. How nice. Okay, so it looks like v1 is going to be simply equal to the integral of this with respect to x. And that's going to be, looks like negative 3/4 x to the fourth. Notice we don't worry about the constant because that would just become part of the complementary solution. Let's go to V2. So V2 prime of x, that's going to equal, again, we have our same denominator. So looks like 2x minus x squared e to the x. And my numerator is e to the x, and then I have my 0 here. 3x squared times x minus 2 e to the x. Now here, it's going to get a little messier. We're going to get, looks like 3x squared times x minus 2 times e to the 2x. And again, factoring that denominator, we're going to get, I'm going to factor out negative x, so it's a little more apparent. So we get a lot of cancellation again. And we get a negative. And we have a 3x. The x minus 2's cancel. One of the e to the x's cancel. I'm left with the e to the x. And so for V2, we have to integrate this. So that's a nice integration by parts problem. So u equals x, dv equals e to the x, a nice forgotten calculus 2 here. Du equals dx, and that should be a dx. V then is going to be equal to e to the x. Okay, so you can follow along there. Sorry about the shadowing, but my light's not cooperating totally. Okay, so this is going to be u times v, so it's going to be x e to the x. Then we subtract off the integral of v du. And I forgot my negative 3 out in front. And so we're going to get v2 is negative 3 times x e to the x minus e to the x. And then simply to get your particular solution, you won't go through all that, you would have to then take that v1 and v2 and plug it back in to here. Notice this is a problem you definitely could not do with undetermined coefficients. Okay, so that finishes things up for section 4.4. And this is where we're going to have the break for exam 2. So I'm going to go ahead and post the material for the next unit. You'll need to pick a time to take the exam. Any time really between now and the week after Easter. So I want to fit whatever your schedules are. The way we're going to do this is I'll have the exam written. You tell me what day you want to take it. I'll email it to you the night before and you return it by the next night. So that way each person can sort of do it on their own schedule. So you'll see that popping up in the Blackboard before too long. So take care, and before long I'll put up some review materials for the exam and also start into putting up materials for Chapter 5. Take care.